So I'm going to continue with problem 36 on page 155. An elastic band is hung on a hook and a mass is hung on the lower end of the band. So you have a band and you have a mass, it's a rubber band. When the mass is pulled downwards and then released, it vibrates vertically. The equation of motion is, so this is the equation of motion of how it vibrates like that, jumps up and down, is equal to 2 cosine t plus 3 sine t for t greater or equal to 0, where s is measured in centimeters and t in seconds. Take the position direction to be downwards. So find the velocity and the acceleration at time t. So the velocity is the derivative. So you have s prime is equal to negative 2 sine t minus 3 cosine t. Right, so that's going to be our velocity, the first derivative. And the acceleration is the second derivative, so s prime prime of t, s prime prime is going to be negative 2 cosine t, then plus 3 sine t. The plus happens because that the derivative of cosine is negative, fine. So then it asks us to graph the velocity and acceleration functions. I'm not going to do that, and okay, I'm not going to do the other problems, but it's going to be that problem. So now let's do problem 37. A ladder 10 feet long rests against a vertical wall. So we have a wall and we have a ladder resting against it. So let phi be the angle between the top of the ladder and the wall. So here we have an angle. And let x be the distance from the bottom of the ladder to the wall. So this is going to be x. If the bottom of the ladder slides away from the wall, so we have that the bottom of the ladder is sliding away from the wall, how fast does x change with respect to, so how fast is x changing with respect to this angle when the angle is equal to 2 pi over 3? So we know that the ladder over here is 10. And we know that sine of an angle is equal to the opposite over hypotenuse, which for us is going to be x, which is the opposite of this angle. The hypotenuse is over 10. So now we can say that x is going to equal to sine of the angle over, times 10. So x is going to be sine of the angle times 10. So the change in x, which is what we're trying to find, because we're trying to find how fast does x change with respect to the angle. So when the angle is a certain amount, how quickly is x changing? So the change in x over the change in the angle is going to be cosine of that angle times 10. So now, and this is the same as f prime of, the angle. F prime of the angle. So now when we take f prime of pi over 3, what we get is cosine pi over 3 times 10. So I'm just going to put in a calculator cosine of pi over 3 is a half times 10, so this is 5. So the change in x, the amount that x over here is changing over the change in the angle, when we put in that the angle is equal to pi over 3, so then the amount that x is changing as the angle is changing is equal to 5. Okay, that's the distance that it's moving away at that point. So now problem 38, an object with weight W is dragged along a horizontal plane by a force acting along a rope attached to the object. So we have a plane, we have an object. So we have an object and we have a rope over here that's pulling the object. If the rope makes an angle, so the rope maybe it does not look exactly like that, but have an object. Anyway, so the rope makes a certain angle with the plane, whatever it is, I don't know. Then the magnitude of the force on the object is going to be u of w times u sine of that angle plus cosine of that angle. Where, so this is some constant, which is the friction of the object with the bottom over here. So it's that constant. So find the rate of change of F with respect to the angle, right? How does the force change with respect to how I hold this rope? So we're going to have the change in F over the change in the angle, and we're going to use the quotient rule. So this is going to be, first we're going to have that sine plus cosine. All of that times, well, w and mu are constant, so we get a 0 up here. So we can just get rid of all this. And then we're going to have minus mu w times u cosine the angle minus sine of the angle all over u sine of the angle plus cosine of the angle squared. So now we're asked to find when is this equal to 0, right? We're asked to find when is the rate of change equal to 0 of the force. So you can just multiply by the bottom over here, so that's 0. So we're trying to find when negative mu w times u cosine of the angle minus sine of the angle is equal to 0, or what we're trying to find is when is this equal to 0. So we're trying to find when this is equal to sine of that. Or in other words, what we're trying to find is when do we have sine of that over u cosine equal to 0, or in other words, when do we have mu tan is equal to 0, or in other words, when do we have that the angle is equal to, sorry, I'm just, when I do this, it's, I guess, easier, yeah, no, because then the mu will not end up on top, sorry. When I do this, I'm just going to say when is mu equal to tan of the angle, or in other words, when is the angle equal to tan inverse of mu, of the constant, and this is when we get 0, so it's based on the friction constant. You're going to find an angle such that when you find the angle, the rate of change of the force is going to be 0 over the angle. So moving the angle a little up or down, it will not really, I guess. So now we're going to have if W is equal to 50, mu is equal to 0.6, draw the graph f as a function of the angle. So I'm actually just going to plot this. So I'm going to pause the video and plot it. So when we graph this, I'm just going to graph 1. We're going to have the x-axis, and we're going to have something that looks like that. And like this, and it just does this like infinitely many times, something like that. And this is the change of the force this is the magnitude of the force. So now the change of the force is given the angle is going to be 0 right here, and when we take tan inverse, we have to restrict it of mu. We have to restrict it because the tan does something like this. Okay, that's a bad picture. Does something like like that, and then it just keeps doing that. So we take the inverse, we'll only get one of them, because we can't have something like that. This is not a function. We'll only get one of these. So, so looking at the graph and the calculator, I see that the place where the graph seems to have a horizontal tangent is 0.54, and tan inverse of 0.6 is equal to 0.54, so it's correct. We can also ignore a lot of these or everything, because we can take the angle to just be in the interval 0 to pi over 2, because after that we're going to just repeat. So we're going to basically get something from here to here, and that's going to be the force given the angle and 0 to pi over 2. So next question is problem 39. It asks us to find the limit as x goes to 0 of sine 3x over x, and we are given on page 149 that the limit, I'm going to use the x over here, as x goes to 0 of sine of x over x is equal to 1. That we know. So in order to find this limit, we can basically, so we're going to use this fact, and we're going to multiply this by 3 and this by 3, right, like that. So now this is the same as 3 times the limit as x goes to 0 of sine 3x over 3x, and this is going to be, because that x over here is anything, right, we can just take 3x to equal x, or to equal u, and change this to u. So this is going to be 3 times 1, so that's going to be our limit. So the next problem, problem 40, asks us to find the limit as x goes to 0 of sine 4x over sine 6x. So what we can do over here, this is going to equal to the limit as x goes to 0. Right, we cannot use the fact that I just stated straight away, because we have over here 4 and over here we have 6. So it's not the same as the limit as x goes to 0 of sine x over x, because over here we have 1x and 1x, and this is equal to 1, but now we need to know what this is equal to. So this is the same as the limit as sine 4x over 4x times 4x over here divided by cosine, oh sorry, not cosine, sine 6x over 6x times 6x over here, right? So you're going to have something like that. So now by the rule A over B divided by C over D equals A D over BC, what we get is that this is equal to sine 4x times 4x times 6x over 4x sine 6x times 6x, like that. Okay, so now we have the rule that if we know that the limit of g of x and f of x exists, then the limit, as let's say x goes to a of g of x times f of x is equal to the limit as x goes to a of g of x times the limit as x goes to a of f of x. This is only if we know that these limits exist. So now, because of this rule, we can say that for the limit, we get that this is equal to the limit as x goes to 0 of sine 4x over 4x times the limit as x goes to 0 of 6x times 4x over sine of 6x times 6x. So this just gives me a 1, right? This becomes a 1. So now we get that. So now we're left with this limit. So let's just erase some of this. So now we are going to break this up again and say that this is going to equal to the limit as x goes to 0 of 6x over sine of 6x times the limit as x goes to 0 of 4x over 6x, right? I basically took this and I broke it off with that. Okay, and this is going to give us, right, the x's cancels and the 4 over 6 cancel. This is going to give us 2 over 3. So now the question is, what is this limit? So let's call that limit y. So let's say that y is equal to the limit as x goes to 0 of 6x over sine 6x. Then 1 over y is going to equal to the limit as x goes to 0, and then we're going to have 1 over 6x over sine 6x, which is going to be the same as, right, you can put a 1 over here, and the sine is going to come up here, and the 6 is going to be here, so this is going to be sine 6x over 6x. So this is going to equal to the limit of sine 6x over 6x, which is equal to 1. So we have 1 over y is equal to 1, so we have y is equal to 1. So this limit is also equal to 1. So this is equal to 1, and in the end we're left with that, 2 over 3. The next problem that they ask us is to find the limit as t goes to 0 of tan 6t over sine of 2t. Well, this is equal to the limit as t goes to 0 of sine of 6 sine of 6t over cosine of 6t all divided by sine of 2t, and this is going to be equal to the limit as t goes to 0 of sine 6t over cosine 6t times sine of 2t, which is the same as the limit as t goes to 0 of sine 6t over sine of 2t times the limit as x goes to 0 of 1 over cosine 6t. Now, by the exact argument that we did before, this is, we can do the exact same steps. It's going to be 3 over 2, because it's basically taking the 6 6 over 2. The same way this example, we had 4 over 6 over here, and the limit ended up being 2 over 3. So here we just take the 6 and the 2, we get 6 over 2, so we get that the limit over here, is 6 over 2, which is 3. And the limit over here, right, so cosine of cosine of 0, cosine of 0 is equal to 1, so this is going to be 1 over 1, so this is going to equal to 1, so the answer is 3. The next problem is problem 42, which asks us to find the limit as x goes to 0 of cosine x minus 1 over sine of x. So what we want is we want to get sine of x over x. So we can say, well, this is going to equal to the limit as x goes to 0 of cosine x minus 1 over x, all divided by sine of x over x, right? Because you just multiply everything by 1 over x, the top and the bottom. And this is going to equal, so over here we get a 1, so this is going to equal to the limit as x goes to 0 of cosine x minus 1 over x. So now on page 151, we're also given the following limit, that the limit as x goes to 0 of cosine x minus 1 over x is equal to 0, right? We're given the following claim. So this is equal to 0, and this over 1, because this is 1, which is equal to 0. So that limit is equal to 0. So the next problem, problem 43, asks us to find the limit as x goes to 0 of sine cosine of x over secant x. Well, this is equal to the limit as x goes to 0 of sine cosine of x over 1 over cosine of x, which is equal to the limit as x goes to 0. And this, again, okay, so this is going to jump up here. We're going to get sine of cosine x times cosine of x. And now we can just plug in our limits. So we're going to get sine. We're going to get sine of cosine of 0 times cosine of 0. Cosine of 0 is equal to 1. So this becomes sine of 1 times 1, or sine of 1. So now our next problem is problem 44, which asks us to find the limit as t goes to 0 of sine squared. This is supposed to be a derivative video, but these are the problems that they are giving me, so I'm just going to do this for now. So this is going to be equal to the limit as t goes to 0 of sine of 3t times sine of 3t over t times t, right? So all we really need to find is the limit as t goes to 0 of sine 3t over t. That's all we're trying to find. So let's take 3t to be equal to u. So then we're going to have t is equal to u over 3. So we can rewrite this in terms of u as the limit as u goes to 0, right? Because if t is going to 0, then u, which is just 3t, is also going to 0. And then this is going to be sine of u over u over 3. This is equal to 3 times the limit, right? The 3 just jumps up over here, times the limit as u goes to 0 of sine of u over u, and this is just going to be 3. But so this is for one of these, but then we multiply it by another 3, so we get 3 times 3 is equal to 9, so the limit of this thing is 9. So now the next problem is problem 45. It asks us to find the limit as x goes to 0 of sine x over x plus tangent x. So this is equal to sine x over x plus sine x over cosine x. And again, we have to think, what are we trying to get to? We're trying to get to sine over x and cosine. Well, let's try mostly to get to sine over x. So if we multiply all this by 1 over x up here and 1 over x down here, what we get is this is equal to the limit as x goes to 0 of sine x over x all over 1 plus sine x over cosine x times x. Well, so this we know what it is, and we can kind of ignore this 1, and we also know what this is. This. So this is going to be equal to 1 over 1 plus 1 over cosine x times 1, right? Because this sine over x is going to give us 1. So you take the limit as x goes to 0 of this, so let's just plug in 0, so we're going to get 1 over 1 plus 1, or a half. So for our next problem, we have the limit as x goes to 0 of sine x squared over x. So we're trying now to get a sine x squared over x squared. That's pretty much what we're trying to do. Well, okay, so then this can, if we multiply the top and the bottom by just x, so this is going to equal to lim as x goes to 0 of sine x squared times x over x squared. We know that this is 1, so we're going to get the limit as x goes to 0 of 1 times x, or we're going to get 0. So I'm going to skip the next problem because it involves pi over 4, which I'm not interested in doing right now. So let's look at the next problem. The limit as x goes to 1 of sine of x minus 1 over x squared plus x minus 2. So what we want is we want to get a sine of x minus 1 over x minus 1, which its limit is going to be 1, and then something else. So x squared plus x minus 2 is equal to, well, we're going to assume x minus 1 times something. So we're going to have an x over here, and so we're going to have x squared minus an x, and we need an x, so we're going to put a plus 2 here, and yeah, this should be x squared minus x plus 2x minus 2. So this is going to equal to the limit as x goes to 1 of sine of x minus 1 over x minus 1 times x plus 2. In other words, this is going to be 1, right, because this is 1 over x plus 2, and we're taking our limit as x goes to 1, and this is now going to be a third. Now they ask us to, they give us identities like tan of x is equal to sine of x over cosine x, and they want us to take cosine x. They want us to take the derivative of both sides to get a new trigonometric identity, which is interesting. So the derivative, so we're told this, the derivative of tan x is secant squared x, and the derivative of sine x, let's look at that. So we're going to have f of x is equal to sine of x over cosine of x. So f prime of x is going to equal to cosine x times cosine x minus sine x times, so this is going to be a plus sine x all over cosine squared of x. So this is cosine squared plus sine squared, which is equal to 1. So this is going to give me 1 over cosine squared x. In other words, we get that secant squared is equal to 1 over cosine squared of x, which is obviously true, right? Because secant of x is equal to 1 over cosine of x, so secant squared is equal to 1 cosine squared, but it's nice that it worked out. Another identity that we know is that secant x is equal to 1 over cosine x. So now let's take the derivative from both sides, and I'm going to use their derivative just so it works out the way they want. So we have that the derivative of secant x is secant tan of x, secant x tan of x, and that's going to be equal to sine, that's going right, cosine times negative 1 is 0 minus, and then we get a negative sine x over cosine squared x, which these are obviously equal, right? Because, well, secant x tan x is the same as 1 over cosine x times sine over cosine x, and that's equal to sine over cosine squared of x. So that identity is true. So then we're given the identity sine of x plus cosine x, and this is a very interesting way of just finding new trigonometric identities. Cotan x over cosecant x. So the derivative of this is going to be cosine x minus sine x. So what's cosine x minus sine x? Well, it's going to be cosecant x times the derivative of 1 minus cotangent. I'm just going to look at what they say cotangent is. So it's going to be 1, wait, is it minus? No, it's plus. So it's going to be negative cosecant squared x, and then minus 1 plus cotangent x times the derivative of cosecant, which is negative cosecant x cotangent x, and we have all this divided by cosecant x squared. And I assume that if you start simplifying this and going back to what it means, you'll just get this. But this is another way to find the identity. Okay, we have 2 more problems left. So we're told that a semicircle with diameter PQ, we have this thing, it has PQ right over there, sits on a isosceles triangle, so something like that, PQR. I'm just drawing a picture that they have to form the region shaped like 2-dimensional ice cream cone, as shown as in the figure. And so we are told if A of the angle is the area of the semicircle, so the area over here is A of this, and B of an angle is the area of the triangle, so that's B of that angle. So we want to find the limit as the angle goes to 0 from the right, and this is the angle that we're talking about, of A, the angle, over B of the angle. And we're given that this is 10 centimeters and this is 10 centimeters. So we know that A of the angle is equal to pi r squared, a half of it, because it's a half a circle. So the area of a circle would be pi r squared, so this is half of that. So what is r? So if you use the definition of sine, we have sine of an angle is equal to the opposite over We can take this triangle first and look at it something like that, and then just cut this right in half. And this is the radius of the circle, and this over here is the angle over 2. And sine. So now what we're trying to do is we're trying to find r in terms of the angle. So we're going to have sine of our angle is equal to the opposite. Sorry, that's a 2. It's equal to the opposite, which is r, over the hypotenuse, which for us is 10, where r is equal to sine pi over 2 times 10. So that's what we get r is. So now we have, let's just erase some of this. Oh, let's just rewrite what we're looking for. Again, what we're looking for is the limit as our angle goes to 0 from the right, because there is no going from the left really. A angle over B angle. So this is going to be half pi, and then we're going to have sine of our angle over 2 times 10. And now what we're doing is we're squaring this. So that gives us A. Now the question is, what is B? So B, it can be written in terms of half of the base of the triangle times its height. So what's the base of the triangle? Well, we already figured that out. It's going to be, this is half of the base. So the entire base is 2 times sine pi over angle over 2 times 10. And now, so that's the base, and we are dividing by this 2. So that gives us that. And what's the height? Well, the height is this. And that can be written, so cosine of an angle is equal to the adjacent over the hypotenuse, which for us is going to be the height over 10, or in other words, and right, this is pi, the angle over 2, because we're only taking half of the angle right over there. So we have that h is equal to cosine pi over 2 times 10. So this is what we have, and this is going to equal to the area in terms of our angle, right? So now our limit, let's rewrite our limit, is going to equal to, so when we square 10 we get 100, when we take half of that we get 50, so it's going to be 50 pi squared sine of that squared over, and then over here we're going to get 100, so get 100, and then that's from that, and then we get sine pi over 2 cosine of that. I'm going to erase all this. So now this is going to equal to a half, and then we can take out a sine squared over here, and then we're going to basically get rid of that, and we're going to have pi squared over, and then over here we're going to get tangent. So we can just write, it's going to be a half, and then tangent pi over 2. And as this goes to 0, tangent goes to 0, right? Because tan of 0 is equal to 0. So this becomes 0. So as this angle goes to 0, the ratio of this area to this area also goes to 0. Okay. I'm not going to do the last problem because I want to move on to the chain rule. So let's just do some problems involving the chain rule. So the first problems 1 to 6, this is on page 161. They ask write the composite function, so we want to take the function and write it in the form of f g x, meaning we want to find this form, meaning identifying the inner function and the outer function. So we want to identify the inner function in terms of u gx and the outer function in terms of y equals f of u, and then find the derivative dy over dx. And we're going to play a lot with different notations just to get a feeling of what is going on. So if we have y is equal to sine 4x, and we take f of x to equal sine of x, and g of x to equal 4x, then we're going to have y is equal to f of g of x, right? Because the f is the sine and the g of x is the 4x. So that's what we're going to get for y. And furthermore, so we can say that 4x is equal to u, and sine of x, let's say, is equal to w. So we're going to have, well, actually not. So we're going to have y is going to be equal to sine of u, right? Because the u is 4x. So now if we take, so let's first look at it. So dy over dx is equal by the chain rule to, so let's write, in order that we actually follow the chain rule, let's write this in the form over here, sine of u, right, because we're plugging in a u, and let's say that this is going to equal to y, right? So again, if we plug in the u over here, we get y is equal to sine of u. So dy over dx is going to be du over, it's going to be dy over du, right? So it's the change in y over the change in u, but then u, if we want to find it in terms of x, we're going to have to then say, and then take du in terms of dx, right? Or in other words, based on the notation with the f, we're going to say that f prime of x is going to equal to let's say that we have big F is equal to this. So we're going to have f prime of x, big F, is going to be equal to f little f prime of x, of gx times g prime of x, where we take the derivative of f, so that's this, and just plug in our g, which is that, and then we take g prime of x, which is the derivative of g of x for this. So let's just write out the solution for our particular problem, right? So we have y is equal to sine 4x, so y prime is going to equal cosine 4x times 4, meaning we take the derivative of sine, keeping the 4x in here, and then we just take the derivative of 4, right? Because again, we're taking big F of x to equal f of g of x, where f of x is going to be sine of x and g of x is going to be equal to 4x. So now f prime of x, which we know is f prime of g of x times g prime of x, well, f prime is just, if anything, is just cosine, and then we just plug in g of x, so we plug in 4x, and then we take the derivative of g of x, which is 4, right? And this, at the same time, again, if we make 4x to equal to u, and then we have y is equal to sine of u, right? That would mean that y is still equal to this because u is equal to 4x. Then we know that dy over dx is equal to first du over dy over du. First dy over du, and then du over dx. Well, what is dy over du? dy over du is just going to be cosine of u. And then du over dx, well, that's du over dx is going to be 4. But we know that u is equal to 4x, so this is going to be cosine 4x times 4. And eventually we'll stop all of this and we'll just look at the function and just think about what is the inner function and the outer function. But for now, it's important to just write all of this out. I guess I'll go until problem 6 doing this, and then I'm gonna, in the next video, I'll just go through a bunch of problems and not like focus on writing out everything out. So now we're gonna have y is equal to 4 plus 3x. So we can take f of x is just going to be equal to the square root of x, and g of x is going to be equal to 4 plus 3x. So big F of x is going to be equal to y, which is equal, is going to be, let's just make it equal to f of g of x, right? So anytime you see an x here, you just plug in a g of x, and this is equal to y, right? So f prime of x, we know, is going to be f prime of g of x times g prime of x, which is equal to y prime. So y prime is going to be taking the derivative of f, so that's a half x to the negative a half, but then plugging in a gx whenever you see an x over here. So what we're going to do over here is we're going to plug in a gx, and then taking the derivative of gx, which is going to be 3. Well, this is equal, if we actually write it out, it's going to be y prime a half, and then gx is 4 plus 3x, then 2 a half, times 3. Similarly, if we use Leibniz's notation, again, we're going to have y is equal to the square root of 4 plus 3x. So let's take u is equal to 4 plus 3x, right? So then we have y is equal to the square root of u. So now let's find dy in terms of dx. Well, that's the same as dy in terms of du times du in terms of dx, right? Well, dy in terms of du, right? We look over here. There's no x, and this is dy. If we take dy in terms of du, we're going to get a half u to the negative a half. And then we want to multiply it by du in terms of dx. So when we take over here du, right, we take a du over here in terms of dx, well, on the other side we just get our derivative, which is 3. So we put a 3 here. Well, we know what u is. U is 4 plus 3x, so that's the same as a half 4 plus 3x, negative a half times 3. Again, we will not have to do this every single time we take the derivative. That will take way too long, but it's to go through a couple of examples like this to just get a sense of what's going on, and then just go through a bunch of examples afterwards. So let's say we have y is equal to 1 minus x squared to the 10x. So again, we can say, well, f of x, big F of x, can equal to little f of g of x, where f of x is equal to x to the 10th power, and g of x is the function inside, which is 1 minus x squared, right? So now this is equal to y. If we plug in, every time we see a g of x over here, we plug in that, then we'll get this. So now f prime of x is going to give us f prime of g of x times g prime of x. Well, so f prime is going to give me 10, and then plugging in our g of x, we're going to get 1 minus x squared to the 9, right? This is going to be the f prime, and then we plugged in our g of x, and g prime of x is negative 2x. Okay, doing this using Leibniz's notation, again we have y is equal to 1 minus x squared. And I honestly believe that learning Leibniz's notation is more important than learning Newton's notation, especially if, like, for differential equations and later chain rules. For multivariable calculus, it's very important. So it's just good to get it over with. So now let's take y is equal to u to the 10, and u is going to be equal to 1 minus x squared, right? So now if we plug this in, right, y again, u to the 10, where u is this, right, we're going to have 1 minus x squared to the 10, which satisfies that. So that's what we're going to write. And again, the reason we need the chain rule is because all the rules that we learned, they work for, like, finding f of x, maybe g of x. But what happens if you have a function inside a function? You have f of g of x. What happens? How do you do this? You can't just take the derivative of f and the derivative of g of x. Like, what allows you to do that? But we know the rule is you take the derivative of f of x, keeping the g of x, and then you take the derivative of g of x. That's just a rule called the chain rule, which makes everything much simpler. Okay, so now dy in terms of dx, right? We're trying to get to x in the end. We're trying to find the derivative of this thing. Well, that's equal to dy over du times du over dx. This is going to get us to dy over dx. Well, so what's dy over du when y is written in terms of u? Well, dy over du is equal to 10u to the 9, which is equal, by what we know the u is, to 10 times 1 minus x squared to the 9. And du over dx is equal, well, du in terms of dx, well, it's going to be negative 2x, right? So then this is going to be equal to that, which is equal to 10, 1 minus x squared to the 9 times negative 2x. Okay, next problem is problem 4, which says y is equal to tangent sine of x. So again, let's take let's only do this one with Leibniz's notation. So let's take y is equal to tan of u. So what is u going to be if y is equal to tan of u? And you see this is a function with just one variable here. It's not a function inside a function, so we can deal with it. We can talk about it. And now u is going to be sine of x. Again, just a single function, one variable. It's not a function inside a function, right? Sine of x squared, this is a function, and then you have another function that it's inside of. So we're trying to avoid those type of situations. We just want a single, simple function. Okay, so now we know that dy over dx is equal to dy over du times du over dx. Well, this is equal, so what's dy in terms of du? Changes in y, well, we look at this, we take the derivative of this, and it's secant squared of u, right? That's the derivative of tangent of u. And what is du over dx? Well, that's the derivative here. It's going to be cosine of x. So we write this out, and now we just replace u when we write it out with sine of x. So we write this out, so it becomes dy over du is equal to secant squared, and now u in terms of x, so we get sine x and then cosine x for here, so we just get cosine x. That's that derivative. Next problem is problem 5. We're going to have y is equal to the square root of sine of x. So let's, again, I'm only going to do this in terms of Leibniz's notation. So let's take y is equal to the square root of x, of u. Okay, very simple function again, one variable. Again, this is a function inside a function. The first function is f of x is equal to the square root of x. And the second function is g of x is equal to sine of x. And then when we have f of g of x, right, a function inside of a function, we get, right, square root of sine of x, which we don't want to deal with. So y is this, and then u is going to equal to sine of x. So again, we have dy over dx is equal to dy over du times du over dx. Well, what's dy over du? So dy over du, that's over here, that's a half u to the negative a half. And what is du over dx? Well, that's cosine x, right? Take the derivative over here. So then we get that this is equal to that, and now we're just going to plug in what we know that u is in terms of x. So we're going to get a half sine x to the negative a half times du over dx, which is cosine x. The problem is problem 6. We have y is equal to sine square root of x. So again, we can say y is going to equal to sine of u. Y is going to equal to sine of u. And u is going to equal to the square root of x. Right? Plugging everything else in, you're going to get y is in terms of x. So again, dy over dx is equal to dy over du times du over dx. Let's do that. So dy over du is equal to cosine u, right? Because dy over du is cosine u. And du over dx, well, that's the derivative over here. It's a half x to the negative a half. So now we're just going to plug in what u is, and we're going to get that this is going to equal to cosine square root of x times 1/2 x to the negative a half. Using Newton's notation, because I have 2 minutes left, we're going to have big F of x. So right, again, we have y is equal to sine square root of x. So we're going to have big F is equal to f of g of x, where f of x is sine of x, and g of x is the square root of x, right? And we can verify f of g of x, right? Take g of x, just put it in here, we're going to have f of the square root of x. So anytime in f where you see x, you're going to put in the square root of x. Also, this is going to become sine of the square root of x, which is equal to y. So big F of x is equal to y. So now we know that f prime of x is equal to f prime of g of x times g prime of x. Well, what's f prime of x? Well, it's cosine x. And what's g prime of x? Well, it is a half x to the negative a half. So when we take f prime of g of x, we're going to take f prime of the square root of x, and that's going to be cosine square root of x. Then when we multiply by g of x, we're just going to get a half x to the negative a half. So finally, just to end this, again, we have a function inside a function, and you can have a function inside a function inside a function, which we'll definitely deal with. But for now, you have a function which is made out of one function inside of another function. That's one function inside of another function. And we cannot just say that f prime of x is equal to f prime of g prime of x. This is not true. Not true. But the rule tells us that if you have a function inside a function, and you have to see it, you know, e to the x, this is one function. This is that. But e to the negative x squared, this is one function. This function, which can be written in terms of f of x, is equal to negative x squared. And another function, which can be written in terms of, let's say, g, well, this will be g, and f of x is going to be e to the x. Now, you might ask, well, x itself is a function, right? You can write, let's look at sine of x. Let's take y is equal to sine of x. Well, we can take f of x is equal to little f of g of x, where f of x is equal to sine of x and g of x is equal to x, right? This is completely reasonable, and then this is going to be equal to y. The chain rule will still say that this is fine. If you do something like this, so let's look at it, right? You're going to have f prime of x is equal to f prime of g of x times g prime of x. Well, f prime of g of x over here will just give me cosine, and then plugging in g of x, you're going to get x. And then the derivative of g of x is just 1, which is just cosine of 1, which is straight up if we just take the derivative of this without worrying about x being a function inside of another function. So the chain rule will still agree with this, but if you have a function over here which is not x, maybe it's x squared, it's the square root of x, so on and so forth, then you have to use the chain rule. And it's always important to figure out what function is inside what, and what happens when you have h and then you have f inside of h and you have g inside of f, something like this. How do you deal with this? And we'll have to learn how to deal with this, but that's for the next video. I hope this was helpful. And the next video and probably the video after that, both are going to be on the chain rule. Yeah.